In 1948, a physicist working at a lightbulb company in the Netherlands sat down and proved that empty space is not empty. He proved it with a formula so clean it fit on a single line. 2 uncharged metal plates placed in a vacuum with nothing between them, no particles, no radiation, no fields, nothing at all, would be pushed together by a force that should not exist, a force that comes from nowhere, a force generated by emptiness itself. His name was Hendrik Casimir, and his prediction was published, peer-reviewed, and eventually confirmed to extraordinary precision. Empty space contains energy. That is not speculation. That is what the math says, and the experiments agree. Before we dive in, if you want to support the channel and get exclusive content on all things space and physics, check out our Patreon. Link is in the description. What nobody knew at the time was that Casimir's little paper would become the birth certificate of the single most catastrophic failure in the history of theoretical physics. Because that same year, 1948, 3 of the most brilliant minds alive, working independently on 3 different continents, figured out how to subtract that energy from the equations of quantum physics. They erased it, set it to 0, pretended it was never there. And their reward for this act of deletion was the most accurate scientific theory ever constructed, a theory whose predictions match experiments to 11 decimal places. They won Nobel Prizes. They became legends. And the energy they erased sat there quietly for 50 years until it came back. When it came back, it produced the worst prediction in the history of science, not wrong by a factor of 2, not wrong by a factor of 1,000, wrong by a factor of 10 to the 120th power. That is a 1 followed by 120 zeros. If you wrote that number out, it would stretch across a page and keep going. To this day, nobody knows how to fix it. And the people who should know, the physicists, the cosmologists, the people who study the fundamental nature of reality for a living, most of them would rather talk about almost anything else. I have been obsessed with this topic for months now. I spent an embarrassing amount of time reading papers about the energy density of nothing. And what I found is a story that I think is one of the most important untold stories in all of science. Not because it is obscure. Every physicist knows about it. But because what it actually implies about the nature of reality is something that the scientific establishment has quietly agreed not to say out loud. And I think you deserve to hear it. This is the story of how physics solved empty space, erased the answer, and then watched in horror as the answer came back, worse than anyone imagined. The story does not start with Casimir. It starts 37 years earlier with a problem that Max Planck did not want to find. In 1911, Planck published what became known as his second quantum theory in a paper titled Eine neue Strahlungshypothese in der Verhandlungen der Deutschen Physikalischen Gesellschaft. He was trying to refine his earlier work on black body radiation, the work that had accidentally launched quantum mechanics in 1900. And in the process, he stumbled onto something that made him deeply uncomfortable. His equations contained a term, 1/2 h nu, that refused to go away. It appeared in the ground state energy of every oscillator in his model. Even at absolute 0, even when you cooled the system to the coldest temperature physically possible, there was still energy left over. Energy you could not extract. Energy that existed for no reason except that the mathematics demanded it. 2 years later, Albert Einstein and Otto Stern gave it a name. In a 1913 paper analyzing Arnold Euchen's experimental data on the specific heat of hydrogen gas at low temperatures, published in Annalen der Physik, they called it Nullpunktsenergie, 0-point energy. And then Einstein, in a letter to Paul Ehrenfest that same November, declared it dead as a doornail. His actual word was Maustaut, stone, cold, dead. He wanted nothing to do with it. But here is the detail that everyone missed at the time. You cannot kill 0-point energy. It is a direct consequence of the Heisenberg uncertainty principle, which would not be formally published until 1927, but was already lurking in the mathematics of the new quantum mechanics. The logic is absolutely ironclad. If a particle sitting at the bottom of a potential well could have exactly 0 kinetic energy, you would know both its position and its momentum with perfect precision. It is at the bottom. It is not moving. But that violates the uncertainty relation. Delta x times delta p must be greater than or equal to h bar over 2. Therefore, the energy of any quantum system can never actually reach 0. The ground state of a quantum harmonic oscillator is 1/2 h bar omega, not 0. Never 0. The vacuum must always jitter. Always. This is not a property of any particular theory or any particular interpretation. It is a consequence of the basic mathematical structure of quantum mechanics itself. You would need to overthrow the uncertainty principle to get rid of it. And the uncertainty principle is the most thoroughly tested foundation in all of physics. And this is where things start to get uncomfortable in a very specific way. Because the electromagnetic field, the field responsible for light, for radio waves, for the forces between charged particles, for essentially every phenomenon you experience in daily life, this field is not a single thing. It is a collection of independent oscillators. Every possible mode of the field, every frequency, every polarization, every direction of propagation, acts as its own separate quantum harmonic oscillator. And each one has a ground state energy of 1/2 h bar omega. And there are an infinite number of modes, which means the total energy of the vacuum, the energy of absolutely empty space with nothing in it, is not small. It is not large. It is infinite. I want you to sit with that for a second. The quantum mechanical description of empty space, the same description that underpins every technology you use, every computer chip, every laser, every MRI machine, every cell phone, says that the energy of nothing is infinity. Not approximately infinity. Not very large. Literally, mathematically, divergently infinite. If you do the sum honestly, without any cutoff, without any tricks, without any regularization, the answer is infinity. If you impose a reasonable cutoff, the answer is finite, but so enormous that it would, as we will see, destroy the geometry of the universe. This should have been a 5-alarm fire in the foundations of physics. It was not. It was treated as a nuisance, a bookkeeping problem. And the reason it was treated that way tells you something important about how physics works in practice, as opposed to how it works in textbooks. Physicists are pragmatists. When a theory produces an answer that is clearly wrong, but the theory also produces other answers that are spectacularly right, the pragmatic response is to find a way to use the right answers and ignore the wrong one. That is exactly what happened with vacuum energy. The infinite energy of the vacuum was subtracted, set to 0 by convention, filed away as an artifact of the formalism. And for several decades, that pragmatic choice appeared to cost nothing at all. Now, in 1916, a German chemist named Wolfgang Nernst took this seriously. Everyone else in the physics community treated zero-point energy as a mathematical artifact, a quirk of the formalism, a constant you can set to zero because only energy differences are measurable anyway. Nernst did not take that comfortable path. He proposed that all of empty space is filled with zero-point electromagnetic radiation, an ocean of it, permeating every point in the universe, and he estimated its energy density at roughly 10 to the 23rd ergs per cubic centimeter. He was the first person to explicitly suggest that the vacuum might be physically, gravitationally real. For this, he was more or less ignored by his contemporaries. The physics community had what seemed like a good reason. If the vacuum really contained that much energy, it should have observable gravitational effects. It should curve space-time according to Einstein's general relativity, which was brand new at the time. It should make the universe behave very differently from what astronomers were seeing. So the reasonable pragmatic assumption was that the energy was a mathematical bookkeeping entry. You subtract it out at the end. Only energy differences matter. Set to zero wherever you like. Problem solved. In 1924, Robert Mulliken provided the first direct experimental evidence that zero-point energy is real by comparing the band spectra of two boron monoxide isotopes, boron-10 monoxide and boron-11 monoxide. The isotopic frequency differences only made sense if zero-point energy existed. Then in 1925, Werner Heisenberg's matrix mechanics paper formally derived zero-point energy as a mathematical necessity of the new quantum theory. The ground state energy is 1/2 h bar omega, period. No interpretation can remove it. But there was one person who followed the gravitational thread all the way to its terrifying end. A young Wolfgang Pauli, working through the implications sometime in the 1920s, performed a back-of-the-envelope calculation that should have changed the course of physics. Using the classical electron radius as a rough ultraviolet cutoff, the wavelength below which he was not willing to sum, Pauli computed what would happen if the vacuum zero-point energy actually interacted with gravity, the way all other energy does. And what he found was that the radius of the universe in Einstein's static model would not even reach to the moon. Think about that for a second. The distance from the Earth to the moon is about 384,000 kilometers. Pauli calculated that if vacuum energy gravitates at its natural value, the entire observable universe, all the galaxies, all the stars, all the light, traveling for billions of years, all of it would be compressed into a volume smaller than the distance you could cover in about a second, at the speed of light. That is what the equations say. That is what the standard theory of quantum fields predicts. And the prediction is not ambiguous. It is not controversial. It is a straightforward sum. Pauli's response was the response of a practical man staring at an impractical number. He decided it was not real. In his 1933 Handbuch der Physik Review article, which was essentially the physics Bible of its era, he wrote that it was more consistent to simply exclude a zero-point energy for each degree of freedom, because this energy, evidently from experience, does not interact with the gravitational field. He dropped the topic entirely from the 1958 revised edition. He died in December of that same year, at 58 years old, in Zurich, of pancreatic cancer, missing the catastrophe his calculation foreshadowed by 4 decades. And this is the part of the story that I personally think is the most underrated. because Pauli did not get the wrong answer. He got the right answer. The math was correct. The conclusion was correct. If vacuum energy gravitates, the universe should be tiny. The universe is not tiny. Therefore, either vacuum energy does not gravitate, which would require new physics that nobody has found in the century since, or the vacuum energy is somehow almost, but not quite exactly, cancelled by something else, to a precision of roughly 1 part in 10 to the 120th power. Pauli saw this. He saw it decades before anyone else articulated it clearly, and he chose to look away. You cannot really blame him. What else was he supposed to do with a result that said the universe should not exist? The answer was too absurd to take seriously. But absurd is not the same as wrong. And Pauli, of all people, should have known that. He was the man who predicted the neutrino in 1930 by proposing a particle so ghostly that he apologized for it, saying he had done something terrible. He had postulated a particle that cannot be detected. The neutrino was detected 26 years later. Pauli knew that physics does not care whether a result is comfortable. But with vacuum energy, he blinked. Eindhoven, Netherlands. 1942. Europe is at war. The Netherlands is under German occupation, and one of the most gifted theoretical physicists in the world is taking a job at a light bulb factory. And it is from that factory that the proof of vacuum energy would emerge, triggered by the most unlikely source imaginable: the physics of colloidal suspensions, basically mayonnaise. Hendrik Casimir was born on July 15, 1909, in The Hague. His father, Hendrik Casimir, was a progressive educational reformer who ran a secondary school while holding an extraordinary professorship in pedagogy at Leiden. Young Hendrik was a prodigy in every sense that word can carry. He enrolled at the University of Leiden in 1926. At 17, completed his first phase exams by 1928 in what his contemporaries described as record time, and began specializing under Paul Ehrenfest. It was Ehrenfest who introduced the young Casimir to Niels Bohr with the memorable words, "I bring you this boy. He has already some ability, but he still needs thrashing." Bohr, characteristically, was delighted. Casimir spent 18 months in Copenhagen with Bohr from 1929 to 31, a period he later described as the most intellectually stimulating of his life. He witnessed quantum mechanics mature from a collection of brilliant, disconnected insights into a unified, theoretical framework. He absorbed Bohr's complementarity philosophy, his legendary indirectness, his maddening habit of speaking in half-finished sentences that somehow contained more physics than most people's completed lectures. Casimir received his PhD at Leiden in November 1931 at age 22. His thesis on the rotation of rigid bodies in quantum mechanics introduced what became the Casimir operator in group theory, a mathematical object that remains a standard tool in representation theory to this day. He then served as Wolfgang Pauli's assistant at ETH Zurich in 1932 and 33, absorbing Pauli's legendary combination of brilliance, cruelty, and occasional kindness. Then, tragedy arrived with absolute brutality. On September the 25th, 1933, his mentor, Paul Ehrenfest, committed suicide in Amsterdam, first shooting his son Wasik, who had Down syndrome, and then himself. Ehrenfest had been suffering from depression, overwhelmed by the feeling that physics had moved beyond his ability to contribute. He had planned the act carefully and written letters to friends and colleagues. Casimir was called back from Zurich. He was 24 years old. His mentor was dead, and he found himself suddenly responsible for Ehrenfest's teaching duties at Leiden until the university could appoint a successor. That successor, Hendrik Casimir, did not arrive until 1934, a year of teaching the classes of a dead man. The loss marked Casimir permanently. He wrote about Ehrenfest decades later with quiet, controlled grief that somehow communicated more emotion than most people manage with tears, and the trajectory of his career shifted in ways that mattered for the history of physics. By 1938, he held a part-time professorship at Leiden, teaching 1 day per week, but the war and the German occupation was strangling Dutch academic life. And in 1942, Casimir accepted a full-time position at the Philips Natuurkundig Laboratorium in Eindhoven. This was the research arm of the Philips Electronics Company, the people who made light bulbs and radios and vacuum tubes and all the mundane consumer electronics that filled European homes. Casimir would remain there for 30 years, rising to research director in 1946, and eventually to the board of management in 1957, overseeing all Philips research operations worldwide. A man who had trained under Bohr, Ehrenfest, and Pauli, who had been present at the absolute center of the quantum revolution, spent the heart of his career making industrial physics work. The irony of what happened next is almost painful in its precision, because the discovery that would make his name immortal in the history of physics, the result that would eventually force the entire field to confront the nature of empty space, came from the most unglamorous problem imaginable. A physical chemist at Philips named Theo Overbeek had noticed that the attractive forces between colloidal particles fell off at large distances faster than Fritz London's theoretical prediction of 1/r2. The sixth power. The interactions were weaker than expected when the particles were far apart. Overbeek suspected that the finite speed of light was involved, degrading the correlation between the electron clouds in the two particles at large separations, and he asked Casimir and his younger colleague, Dirk Polder, to work out the mathematics properly. Polder, born August 23, 1919, also in The Hague, was a Philips researcher who would spend his career in industrial physics. Together, he and Casimir published The Influence of Retardation on the London van der Waals Forces in Physical Review on February 15, 1948. It was a grinding piece of perturbative quantum electrodynamics. Dozens of pages of intricate calculation. Evgeny Lifshitz, himself no stranger to difficult calculations, later described their approach as laborious and lengthy. The result was important. At large separations, the van der Waals force transitions from 1/r to the 6th to a weaker 1/r to the 7th, because the finite speed of light prevents the electron clouds from correlating instantaneously. Overbeek's intuition was confirmed. Pay attention to this next detail, because it explains everything that follows, and I think it might be the single most consequential mumble in the history of science. Casimir mentioned his results to Niels Bohr during a visit to Copenhagen, and Bohr, in that way he had of appearing to be half asleep while his brain operated at a level few humans have ever reached, thought for a moment and mumbled something about 0-point energy. That was it. Not a paper, not a calculation, not even a complete sentence by most accounts. A mumble. An offhand remark from an old Danish physicist who had the peculiar gift of being right about things he could not quite articulate. and it detonated in Casimir's mind like a depth charge. Casimir realized you could bypass the entire laborious QED perturbation calculation, all the multipole expansions, all the retardation integrals, everything, and reformulate the problem from scratch in terms of the vacuum's zero-point energy. Forget atoms, forget electron clouds. Think instead about what happens to the electromagnetic field between two parallel perfectly conducting plates in a vacuum. Between the plates, only those electromagnetic modes whose wavelengths fit an integer number of half wavelengths into the gap are permitted. These are the standing wave modes. Outside the plates, all wavelengths exist freely. That means there are fewer vacuum fluctuation modes between the plates than in the surrounding space. The zero-point energy density between the plates is lower than outside, and that difference in energy density produces a net inward pressure. The vacuum literally pushes the plates together. Nothing pushes them. Emptiness has force. The paper, published later in 1948 as On the Attraction Between Two Perfectly Conducting Plates in the Proceedings of the Koninklijke Nederlandse Academie van Wetenschappen, was 3 pages long. 3 pages. Compared to the dozens of pages of the Casimir-Polder paper, which required elaborate quantum field theory machinery to reach its result, the vacuum energy derivation was almost laughably brief. The formula for the force per unit area is pi squared times h bar times c divided by 240 times d to the 4th power, where d is the plate separation. It contains only Planck's reduced constant and the speed of light. The electron charge does not appear. The masses of particles do not appear. It is not a property of any particular particle or any particular interaction. It is a property of empty space itself. At a separation of 1 micrometer, the predicted force on 1 square centimeter of plate is about 1.3 times 10 to the negative 7th newtons. That sounds negligibly small, but forces scale as the 4th power of distance. At 10 nanometers, the force reaches approximately 1 atmosphere of pressure. From nothing, empty space, with absolutely nothing between 2 metal plates, generating a force equal to the weight of the entire column of air above your head from sea level to the edge of the atmosphere. And no, I am not making that up. That is what the equation says. That is what the experiments confirm. When Casimir told Pauli about the result, Pauli called it absolute nonsense. The same Wolfgang Pauli who had calculated in the 1920s that vacuum energy would compress the universe to smaller than the moon. The same man who knew better than almost anyone alive that the vacuum is not truly empty. Even he refused to accept that the vacuum could push physical objects around, which tells you something about how deeply the entire physics community had committed to the comfortable fiction that vacuum energy was merely a bookkeeping artifact with no physical consequences. Experimental confirmation was agonizingly slow. Marcus Sparney at Philips attempted the measurement in 1958 using flat metal mirrors and a spring balance. The technical challenges were staggering. Maintaining perfect parallelism between 2 plates at micrometer separations is a nightmare of precision engineering. Electrostatic charges on the surfaces can easily mimic or overwhelm the Casimir force. Surface roughness at the nanometer scale changes the effective geometry. Sparney's famous conclusion was that his results did not contradict Casimir's theoretical prediction, which is physicist code for the error bars were so large that the result was essentially inconclusive. The definitive measurement came almost half a century after the prediction. In January 1997, Steve Lamoureux at the University of Washington published demonstration of the Casimir force in the 0.6 micrometer range in Physical Review Letters. He solved the parallelism problem elegantly by using a gold-coated spherical lens near a flat plate attached to a torsion pendulum. The sphere plate geometry eliminates the need for perfect alignment and has a known mathematical relationship to the plate-plate case through the proximity force approximation. Lamoureux confirmed Casimir's prediction to within approximately 5%. Then, in November 1998, Umar Mohideen and Anushree Roy at UC Riverside pushed the precision to roughly 1% using an atomic force microscope, measuring the force at separations as small as 1/10 of a micrometer. Their paper in Physical Review Letters was definitive. The Casimir force is real. It matches the 1948 prediction. Empty space exerts a measurable, physical, laboratory-verified force on material objects. Casimir lived to see his prediction confirmed with precision he probably never expected. He died on May 4th, 2000, in Hees, Netherlands, at age 90. He received the Matteucci Medal, the George E. Paquet Prize, foreign memberships in the Royal Society and the US National Academy of Sciences, and somewhere between 6 and 8 honorary doctorates. He never received a Nobel Prize. I personally think this is one of the great injustices in the history of physics awards. The man who proved that emptiness has energy, working from a light bulb factory in occupied Holland, using an insight triggered by an old man's mumble, deserved better than he got. But there is a twist that complicates the picture, and most popular accounts leave it out because it muddies the narrative. In 2005, physicist Robert Jaffe at MIT published a paper in Physical Review D, arguing that the Casimir effect can be formulated entirely without reference to zero-point energies at all. You can derive the force using source theory, treating it as arising from retarded van der Waals interactions between the charges in the conducting plates. Jaffe wrote that the Casimir effect gives no more or less support for the reality of vacuum energy than any other one-loop effect in quantum electrodynamics. Whether the Casimir effect truly proves vacuum energy is real, or whether the zero-point energy picture is just one convenient way of computing a force that has other explanations, remains an open interpretive question to this day. So even the proof is contested. And that ambiguity matters enormously because the consequences of vacuum energy being physically real are, as we are about to see, almost unthinkably severe. Now here is where the story takes a turn that connects the light bulb factory in Eindhoven to the deepest crisis in modern physics. Because while Casimir was calculating the force of nothing, the most brilliant quantum physicists in the world were simultaneously building the mathematical machinery to erase that nothing from the equations entirely. And neither side knew what the other was really doing to the future of physics. June 2nd, 1947, the Rams head in Shelter Island, New York. 24 physicists arrive for a 3-day conference that would reshape the foundations of quantum theory. The organizer, Duncan McInnes of the Rockefeller Institute, had spent a grand total of $850 on the whole event. On the way to the inn, the physicists' bus received a police escort across Long Island, red lights cleared, a banquet thrown by a local Chamber of Commerce member who believed the atomic bomb had saved his life in the Pacific Theater. The American Physical Society later wrote that at that moment, physics may have reached the apogee of its public reputation in this country. They were not wrong. The bomb had made physicists into celebrities and prophets. Within a decade, that status would sour. But in June 47, they were gods. The star of the conference was Willis Eugene Lamb Jr., born July 12, 1913, in Los Angeles, PhD under J. Robert Oppenheimer at Berkeley in 1938, wartime service, mastering microwave radar technology at Columbia's Radiation Laboratory. Lamb was that rare creature in 20th century physics, a theorist who had become a first-rate experimentalist, converting wartime radar instruments into tools for probing the structure of the hydrogen atom with unprecedented precision. Working with his graduate student, Robert Curtis Rutherford, Lamb had measured the energy difference between two specific quantum states of hydrogen, the 2s1/2 state and the 2p1/2 state. These two states share the same principal quantum number and the same total angular momentum. According to the Dirac equation, published in 1928, they should have exactly the same energy. The Dirac equation is one of the most beautiful and successful equations in all of physics. It predicted antimatter before it was discovered. It explained the spin of the electron without needing to postulate it. And it said, unambiguously, that these two hydrogen states are degenerate. They are not. Lamb found the 2s1/2 level sitting above the 2p1/2 by about 1058 megahertz. In energy units, roughly 4.4 times 10 to the negative 6th electron volts, a tiny number in absolute terms, but a number that should have been exactly zero. The technique was ingenious, exploiting the metastability of the 2s1/2 state, which has a lifetime of about 1/10 of a second compared to the nanosecond lifetimes of typical excited states. The 3-page paper, Fine Structure of the Hydrogen Atom by a Microwave Method in Physical Review, August 1st, 1947, quietly demolished a prediction of one of the most celebrated equations in physics. The cause of the shift is the vacuum. The zero-point fluctuations of the electromagnetic field jostle the electron in its orbit, causing it to undergo rapid random jittering that smears its effective position over a tiny region. Theodore Welton worked out the physical picture quantitatively in his 1948 paper. The smearing affects s-state electrons differently from p-state electrons because s-states have a non-zero probability of being found right at the nucleus, while p-states do not. The asymmetric smearing shifts the energy levels apart by exactly the amount Lamb measured. The vacuum, the supposedly empty space inside a hydrogen atom, was directly measurably affecting the energy structure of matter. The legendary calculation happened on a train. After Shelter Island ended on June 4th, Hans Bethe rode from New York to Schenectady, and on that train, using the discussions from the conference and his own encyclopedic knowledge of atomic physics, he completed a non-relativistic estimate of the Lamb shift. He obtained 1040 megahertz. The measured value was 1058. 2 pages, 12 equations, close enough to prove the vacuum was responsible. Freeman Dyson later captured what made Bethe extraordinary, saying you never needed to look up a number in a table because he knew them all. Bethe carried the physical constants of the universe in his memory, the way some people carry phone numbers. Lamb himself grew wonderfully contrarian in later years. He became famous for his skepticism about the photon concept. In a 1995 paper titled Antiphoton in Applied Physics B, he wrote that in his view, there is no such thing as a photon and proposed, apparently with some seriousness, that a license should be required for anyone wanting to use the word. He won the 1955 Nobel Prize in Physics, shared with Polycarp Kusch. So by June 1947, the vacuum had forced itself into the experimental data. The Lamb shift proved that vacuum fluctuations are physically real and have measurable consequences. You could see the moving energy levels around inside atoms. But calculating the shift required confronting the infinities that had been haunting quantum electrodynamics since the 1930s. Every attempt to compute the electron's interaction with its own electromagnetic field produced infinity. The self-energy integral diverged. The vacuum polarization integral diverged. And the total vacuum energy, the sum of all point contributions from all field modes, diverged as the fourth power of whatever momentum cutoff you imposed. The theory was producing infinities everywhere, and the Lamb shift was the experimental result that made it impossible to keep ignoring them. 3 physicists on 3 continents solved the crisis simultaneously, and understanding what they actually did, not the textbook version, but the real version, is essential to understanding why physics is in crisis today. Julian Schwinger, born February 12, 1918, in New York, was a prodigy of almost frightening proportions. He enrolled at the City College of New York. At 14, he published his first physics paper. At 16, Isidore Rabi recruited him to Columbia, where he earned his PhD at 21. During the war, he worked on radar at MIT's Radiation Laboratory, turning the mathematical tools of nuclear physics to the practical problem of microwave waveguide design. By December 1947, just months after Shelter Island, Schwinger had calculated the electron's anomalous magnetic moment to first order, a correction of alpha over 2 pi above the Dirac prediction, where alpha is the fine structure constant. This works out to about 0.1%. He presented his full covariant renormalization framework at the Pocono Conference in late March 1948, in a presentation that has become legendary. 8 hours, no notes, a display of mathematical architecture so perfectly organized and so relentlessly detailed that few in the audience could follow every step, but all recognized they were witnessing something new. Richard Feynman presented next, and it was, by all accounts, a catastrophe. Coming after Schwinger's immaculate marathon, Feynman introduced his path integral approach and his diagrams, those strange little pictures with lines and loops and arrows that would eventually become the universal visual language of particle physics. But at Pocono, nobody understood them. Niels Bohr, elderly and authoritative, raised his hand and objected that space-time trajectories violated the Heisenberg uncertainty principle. Dirac kept interrupting to ask whether the theory was properly unitary. Edward Teller raised formal mathematical objections. The diagrams looked like doodles on a cocktail napkin. As Feynman recalled years later, he felt like nobody understood a word. His revolution was rejected on first contact with the establishment. Meanwhile, in bombed-out post-war Tokyo, Shinichiro Tomonaga had independently reached the same destination by a completely different path. Born March 31, 1906 in Tokyo, Tomonaga developed what he called a super many-time theory that made QED calculations finite. He published the core ideas in 1943 in Japanese, in a journal that Western physicists could not read. An English version appeared in 1946 in the first issue of Progress in Theoretical Physics. His work had been done in wartime isolation, under conditions of extraordinary material deprivation, without any knowledge of what Schwinger and Feynman were doing on the other side of the Pacific. The unification came from Freeman Dyson, a 25-year-old British mathematician at Cornell, who possessed the rare ability to understand both Schwinger's formal operator methods and Feynman's intuitive space-time pictures. His 1949 paper, The Radiation Theories of Tomonaga, Schwinger, and Feynman in Physical Review, proved the mathematical equivalence of all three approaches. A second paper demonstrated that the renormalization procedure works to all orders of perturbation theory, that no new types of infinities appear in higher order calculations. Tomonaga, Schwinger, and Feynman shared the 1965 Nobel Prize in Physics. Dyson, widely believed to deserve inclusion, was excluded by the three-person limit. He lived to 96 and never won a Nobel. Now, here is what matters for this story. What renormalization actually does. Not the textbook story, the real story. Because the textbook story is that renormalization solved the infinity problem. It did not. It performed the most successful act of mathematical denial in the history of science. In quantum field theory, every mode of the electromagnetic field is a quantum harmonic oscillator with a ground state energy of 1/2 h bar omega. Summing over all modes, all frequencies from 0 to infinity, all polarizations, all directions of propagation, gives a total vacuum energy that diverges. The sum does not converge. It does not approach a finite number. It grows without limit. If you impose a momentum cutoff at the Planck scale, roughly 10 to the 18th GeV electron volts, which is the energy scale where quantum gravitational effects should become important, the predicted vacuum energy density comes out to approximately 10 to the 96th kilograms per cubic meter. If you do not impose any cutoff at all, the answer is infinity, not a large finite number, actual mathematical infinity. This is not a subtlety or a technicality. This is the central equation of quantum field theory, telling you that the energy of empty space is either infinite or so enormous that it would obliterate the geometry of the universe. And the theory that produces this absurd answer is the same theory that correctly predicts the magnetic moment of the electron to 11 decimal places. The theory is simultaneously the most accurate and the most catastrophically wrong thing humans have ever created. Renormalization handles the vacuum energy by normal ordering the field operators, which is mathematically equivalent to subtracting the entire infinite vacuum energy and redefining the ground state to have exactly zero energy. Think of it this way. Imagine you are trying to measure the height of waves on the ocean. The ocean has a depth, thousands of meters of water beneath those waves, but you do not care about the depth. You only care about the waves. So you set your measuring device to 0 at the average surface level and measure fluctuations above and below that. The absolute depth of the ocean is irrelevant for measuring wave heights. Renormalization does essentially the same thing for energy. It sets the 0 at the vacuum level and measures excitations above it. The absolute energy of the vacuum, like the depth of the ocean, is subtracted away as irrelevant. As Feynman explained in his 1965 Nobel lecture, the infinite energy from summing 0-point energies can be removed simply by changing the 0 from which energy is measured. In non-gravitational physics, this is perfectly valid. Only energy differences are physically measurable. Add an infinite constant to every energy level, and all the differences stay the same. Your predictions for scattering amplitudes, for decay rates, for magnetic moments, all remain unchanged. QED's prediction for the electron's anomalous magnetic moment, the G-2 value, agrees with the measured value to better than 1 part in 10 billion. That is like predicting the distance from New York to Los Angeles and getting it right to within the width of a human hair. The theory works with a precision that borders on the miraculous. But here is the catch, and it is a catch so severe that it threatens the foundations of modern physics. The ocean analogy breaks down the moment you include gravity. For waves on the ocean, the absolute depth of the water genuinely does not matter. Waves propagate the same way whether the ocean is 1 kilometer deep or 10. But in general relativity, the analogy fails completely. Because in Einstein's theory, all forms of energy gravitate. All of them. There are no exceptions and there are no opt-outs. Einstein's field equations say that the geometry of space-time, the shape of reality itself, is determined by the total stress energy tensor, and vacuum energy contributes to that tensor on equal footing with every other form of energy. The absolute depth of the ocean matters for gravity. You cannot subtract it and pretend it does not exist, because gravity does not recognize your bookkeeping conventions. Gravity couples to everything, including the energy of the vacuum, whether you have subtracted it from your particle physics calculations or not. This means that when Schwinger, Feynman, and Tominaga deleted the vacuum energy from QED, they were doing something that is completely justified in particle physics and completely illegitimate in cosmology. The deletion works perfectly for calculating how electrons scatter off photons. It fails catastrophically by 120 orders of magnitude the moment you ask what the vacuum does to the shape of the universe. They subtracted the depth of the ocean because they only cared about the waves. But gravity cares about the depth, and the depth, when you calculate it, is large enough to crush the universe into a point. And the men who built the theory knew it was not on solid ground. The descent was not hidden. It was public. It was persistent, and it came from the very people who had created the theory. Paul Dirac, born August 8th, 1902, in Bristol, the man who unified quantum mechanics with special relativity, who predicted the positron 2 years before it was discovered, who held Newton's Lucasian chair at Cambridge for 37 years, spent his last decades in open, vocal revolt against renormalization. Dirac was legendarily taciturn. His Cambridge colleagues defined a unit called a Dirac, meaning 1 word per hour. When a student said he did not understand an equation, Dirac replied, "That is a statement, not a question," and moved on. When Niels Bohr complained that Dirac never said anything, Dirac is reported to have replied, "I was taught that one should not speak unless one can improve upon the silence." But on renormalization, Dirac was neither silent nor diplomatic. In 1975, lecturing at the University of New South Wales in Australia, he said with characteristic precision, "I must say that I am very dissatisfied with the situation because this so-called good theory does involve neglecting infinities which appear in its equations, neglecting them in an arbitrary way. This is just not sensible mathematics. Sensible mathematics involves neglecting a quantity when it is small, not neglecting it just because it is infinitely great and you do not want it." His last paper, published in 1984, the year he died, was titled "The Inadequacies of Quantum Field Theory." In it, he wrote that the excessively good agreement with experiment does not prove the theory correct. The paper ends with Dirac saying he had spent many years searching for a proper Hamiltonian that would make quantum field theory mathematically rigorous, that he had not found it, and that he hoped others would continue the search. He died on October 20th, 1984, in Tallahassee, Florida. The search continues. Nobody has found it. Feynman, who was temperamentally the polar opposite of Dirac in almost every respect, reached the same unsettling conclusion by a different emotional route. In his 1985 popular book, QED, The Strange Theory of Light and Matter, he described renormalization as a shell game and a dippy process, writing that having to resort to such hocus pocus has prevented us from proving that the theory of quantum electrodynamics is mathematically self-consistent. He then added, with the bluntness that made him Feynman, that he suspected renormalization is not mathematically legitimate. In his Nobel lecture 20 years earlier, he had called it simply a way to sweep the difficulties of the divergences of electrodynamics under the rug. I mean, think about that for a second. The two men who won Nobel Prizes for making renormalization work, both publicly, in print, declared that it is not legitimate, and the specific quantity they swept under the rug, the specific infinity they subtracted and declared to be zero, was the energy of the vacuum, the same energy Casimir proved exerts a physical force, the same energy poorly calculated would destroy the universe. Kenneth Wilson, born June 8, 1936, in Waltham, Massachusetts, provided a partial philosophical rescue in the early 1970s. With his development of the renormalization group, Wilson showed that physical theories naturally change their character as you examine phenomena at different length scales, and that the infinities in QED arise from the naive and incorrect assumption that a theory valid at low energies remains valid at arbitrarily high energies. Stop making that assumption. Treat QED as an effective theory valid within a certain energy range, and the infinities become artifacts of overreach rather than symptoms of fundamental disease. His mentor, Hans Bethe, had protected Wilson during years at Cornell when he was publishing very little, insisting the department grant him tenure by saying simply, "This man is deep." Wilson won the 1982 Nobel Prize in Physics, and his framework is now the standard philosophical foundation for understanding quantum field theories. But Wilson's insight, beautiful as it is, does not solve the vacuum energy problem. It makes renormalization philosophically respectable within particle physics. It tells you that QED is an effective theory, valid at accessible energies, and that you should not expect it to give sensible answers about physics at the Planck scale, any more than you should expect fluid mechanics to describe individual water molecules. That is a wise and useful attitude. But gravity does not care about your effective field theory's stated range of validity. Gravity couples to the total vacuum energy at whatever energy scale in whatever effective theory, regardless of whether you have defined it away for the purposes of particle physics. The energy is still there as far as gravity is concerned. It still curves space-time. It still has cosmological consequences. And here is the thing that I think makes this story different from every other unsolved problem in physics. This is not a case where we have two theories that give different predictions and we need an experiment to tell us which one is right. We have already done the experiments. Both theories, quantum field theory and general relativity, are confirmed. They are both right. They are both the most precisely tested theories in the history of science, and they give answers that differ by 120 orders of magnitude when you ask them the simplest possible question about the vacuum. This is not a conflict between a good theory and a bad theory. It is a conflict between two spectacular theories. and the conflict has been sitting there unresolved for nearly 60 years. The person who first proved exactly how catastrophic the conflict really is was a man who taught himself physics from library books and never attended a university lecture as a registered student. And the person who proved exactly how loudly it would eventually detonate was a man who never went to college, Yakov Borisovich Zel'dovich. Born March 8, 1914, in Minsk, graduated high school at 15, got a job as a laboratory assistant at 17 at the Institute of Chemical Physics in Leningrad, washing glassware and calibrating instruments while sneaking looks at the theoretical papers the senior researchers left on their desks. He attended some university lectures from 1932 to 34 without ever formally enrolling or receiving a degree, because he was too busy actually doing physics to bother with the bureaucratic requirements of student registration. He earned his Candidate of Sciences, the Soviet equivalent of a PhD, from Leningrad State University in 1936, bypassing the undergraduate degree entirely because his already published research made the formality irrelevant. He eventually became an academician, the highest rank in Soviet science, a title that carried with it a prestige and authority comparable to a British peerage, a man with no college degree, holding the most distinguished scientific title his country could offer. I find that detail extraordinary, and I wanted to make sure you heard it clearly, because it matters for what comes next. In the 1940s, Zel'dovich became a central figure in the Soviet nuclear weapons program. He served as the first head of the theoretical division at the secret nuclear city Arzamas 16, deep in the forests east of Moscow, where the Soviet hydrogen bomb was developed in direct competition with the American program at Los Alamos. The work was classified at the highest level. Zel'dovich could not travel abroad, could not publish freely, and could not discuss what he did. He was awarded the title Hero of Socialist Labor 3 times, an honor so extraordinarily rare that in the entire history of the Soviet Union, only a handful of individuals received it even once. 3 times meant that the Soviet state considered him one of the most valuable human beings in the country. In the early 1960s, apparently having decided that designing thermonuclear weapons was no longer sufficiently intellectually challenging, Zel'dovich pivoted to astrophysics with the same explosive creativity he had brought to bomb design. He proposed, independently of Edwin Salpeter at Cornell, that accretion disks around supermassive black holes power quasars, those blindingly luminous objects at the centers of distant galaxies that had been baffling astronomers since their discovery in the late 50s. He predicted the Sanyaev-Zel'dovich effect with his student Rashid Sanyaev in 1969, the distortion of the cosmic microwave background radiation as it passes through galaxy clusters, which has since become one of the most important tools in observational cosmology. And during Stephen Hawking's landmark 1973 visit to Moscow, Zel'dovich and his student Alexei Starobinsky explained to Hawking in Zel'dovich's apartment that rotating black holes should spontaneously emit particles through a process related to the Unruh effect. That conversation directly inspired what became known as Hawking radiation, one of the most celebrated theoretical predictions of the late 20th century. Hawking later wrote about the encounter with evident admiration. Zel'dovich died in December 1987 at 73, after decades as one of the most productive and wide-ranging physicists in the world. He published over 500 scientific papers across fields ranging from combustion chemistry to nuclear physics to cosmology. In 1967, Zel'dovich published a short paper in Jet P Letters titled Cosmological Constant and Elementary Particles, with an extended version following in 1968 in Soviet physics, Aspecki. The argument was simple in its statement and devastating in its implications. The vacuum state of any quantum field theory must be Lorentz invariant. It must look the same to all observers, regardless of their velocity. This is not an optional requirement. It follows from the fundamental symmetries of special relativity, which are built into the structure of every quantum field theory we have. And this Lorentz invariance constrains the stress-energy tensor of the vacuum to be proportional to the metric tensor, which means the vacuum has the equation of state P equals negative rho c squared, negative pressure. Pressure equal in magnitude to the energy density but opposite in sign. And this equation of state is mathematically identical to the cosmological constant term that Einstein had introduced into his field equations in 1917 and later abandoned in what may or may not have been embarrassment. The cosmological constant deserves its own chapter in this story, because the popular version is wrong and the real version is more revealing. On February 15, 1917, Albert Einstein published Kosmologische Betrachtungen zur allgemeinen Relativitätstheorie in the Proceedings of the Prussian Academy of Sciences. The paper had a specific motivation. Einstein believed, as virtually everyone did at the time, that the universe was eternal and static, not expanding, not contracting, just sitting there unchanging on the largest scales. But his own field equations of general relativity would not allow it. A static universe filled with matter would collapse under its own gravity. Something had to push back. Einstein's solution was to add a new term to his field equations, the cosmological constant, represented by the Greek letter lambda, introduces a repulsive force proportional to distance. At short ranges, it is negligible. At cosmological scales, it can balance the attractive pull of gravity, producing the static universe Einstein wanted. As Willem de Sitter, one of the few physicists who immediately grasped the implications of general relativity, later put it, what is it then that causes the expansion? Who blows up the India rubber ball? The only possible answer is the lambda does it. When Edwin Hubble published his observations in 1929, showing that galaxies are receding from us and velocities proportional to their distances, the entire motivation for the cosmological constant evaporated. If the universe is expanding, you do not need a repulsive force to prevent collapse. The expansion already prevents it. Einstein dropped lambda from his equations in a 1931 paper and again in a 1932 joint paper with de Sitter. In a remarkable 1947 letter to Georges Lemaitre, the Belgian physicist and priest who had independently derived the expanding universe solution, Einstein wrote that since he had introduced the term, he always had a bad conscience about it, and that he found it very ugly indeed that the field law of gravitation should be composed of two logically independent terms connected by addition. Now, the famous story that Einstein called the cosmological constant his biggest blunder has a complicated provenance. George Gamow, the brilliant but notoriously unreliable Russian-American physicist, first reported the quote in a 1956 Scientific American article, and then again in his 1970 autobiography, My World Line. Historians have argued about its authenticity ever since. Mario Livio, in his 2013 book, Brilliant Blunders, concluded that Einstein probably never said it, noting Gamow's well-documented tendency to embellish stories for dramatic effect. But in 2018, physicist and historian Cormac O'Rafferty published Research in Physics in Perspective, presenting what I think is compelling counter-evidence. John Archibald Wheeler, one of the most respected American physicists of the 20th century, and nobody's fool, independently recalled hearing Einstein say to Gamow in the doorway of the Institute for Advanced Study in Princeton, "That was my biggest blunder of my life." Ralph Alpher, Gamow's former student, corroborated the sentiment. The scholarly consensus has shifted toward accepting that Einstein likely expressed the idea, even if Gamow may have polished and dramatized the English phrasing. But whether Einstein said it or not matters far less than what happened next. Because when Zel'dovich connected vacuum energy to the cosmological constant in 1967, he transformed the problem from a curiosity of quantum field theory, an infinity that could be safely ignored in particle physics, into a crisis of cosmology. Because now you could actually measure what the vacuum energy should be doing to the universe and compare it to what it actually does. This matters because now you can do the comparison directly. The theoretical prediction, using quantum field theory with a Planck scale momentum cutoff, gives a vacuum energy density of approximately 10 to the 96 kilograms per cubic meter. The observed vacuum energy density, measured by the Planck satellite and calibrated against Type Ia supernova distances, is approximately 5.96 times 10 to the negative 27th kilograms per cubic meter. The ratio between prediction and observation is approximately 10 to the 123rd power. Let me try to make that number real for you, because at a certain point, large numbers stop being numbers and just become noise. There are roughly 10 to the 80th atoms in the observable universe. Every atom, in every star, in every galaxy, in everything you can see with the most powerful telescopes ever built, adds up to 10 to the 80th. The vacuum energy discrepancy is 10 to the 43rd times larger than that number. It out-absurds the number of atoms in all of existence by a factor that is itself incomprehensibly vast. Here is another way. Imagine predicting the weight of a newborn baby. You run your calculation, and instead of 7 or 8 pounds, you get not the mass of the Earth, not the mass of the Sun, not the mass of the entire Milky Way galaxy with its 400 billion stars, but a number that exceeds the mass of the entire observable universe by a factor of roughly a trillion. That would still be a smaller error than the vacuum energy prediction. Or think about precision. If the cosmological constant were even a few hundred times larger than its observed value, not 10 to the 120th times larger, just a few hundred, galaxies could never have formed. The expansion would have been too rapid for gravity to pull matter together into the structures we see everywhere in the sky. Every galaxy, every star, every planet, every molecule of DNA exists because the vacuum energy is tuned to within roughly 1 part in 10 to the 120th of what our best theory says it should naturally be. That is not a small amount of fine-tuning. That is the most precise fine-tuning of any parameter in all of known physics, and nobody can explain it. Or go back to Pauli. If the vacuum energy were as large as quantum field theory predicts, space itself would curve so violently that the entire observable universe would fit inside the distance from the Earth to the Moon. No galaxies, no stars, no atoms, no structures of any kind. Just space folding in on itself, too curved for anything recognizable to form. The fact that you are here, reading this, breathing, thinking, is evidence that something has reduced the vacuum energy from its natural value by 120 orders of magnitude. What that something is, nobody knows. Now I need to be careful here and honest with you about something. because there is a misconception about this number that circulates everywhere, and I think getting it right matters. The 10 to the 120th figure, the one that gets cited as the worst prediction in physics, comes from using a hard momentum cutoff at the Planck scale. That cutoff actually violates Lorentz invariance, which is ironic given that Lorentz invariance is the very property that makes vacuum energy behave like a cosmological constant in the first place. Sabine Hossenfelder has argued persuasively that if you use proper dimensionally regularized calculations with the actual masses of known standard model particles, the mismatch is more like 10 to the 55th or 10 to the 60th. The electroweak contribution alone, which is firmly grounded in physics, confirmed by the Higgs boson discovery at CERN in 2012, gives a discrepancy of about 55 orders of magnitude. Hossenfelder has gone further, arguing that calling this the worst prediction in physics is misleading, because the cosmological constant is technically a free parameter in general relativity, and the assumption that quantum vacuum energy should determine its value is itself an unverified assumption about quantum gravity that nobody has proven. I think she has a real point, and I wanted to present it fairly. But I also think it matters less than it might seem, because even the conservative number, 55 orders of magnitude, represents a failure of understanding so colossal that nothing else in the history of any science comes within shouting distance. 55 orders of magnitude means the prediction is wrong by a factor of 10, followed by 54 zeros. And the fact that the physics community cannot even agree among themselves on whether the error is 60 orders of magnitude or 120 is itself a deeply telling sign of how poorly understood this problem is. 60 orders of magnitude or 120, the conclusion is the same. Something is catastrophically, fundamentally, profoundly wrong with our understanding of empty space. And all of that remained theoretical until 1998. Until that year, you could plausibly maintain the hope that the vacuum energy is exactly zero, precisely cancelled by some unknown symmetry mechanism, and the whole cosmological constant problem would reduce to the somewhat less terrifying question of identifying that symmetry. That comfortable escape hatch was sealed shut in a single year by two rival teams of astronomers who were not even looking for vacuum energy and who were deeply surprised by what they found. The Supernova Cosmology project was founded in 1988 at Lawrence Berkeley National Laboratory by Saul Perlmutter, a young physicist who had the idea of using type Ia supernovae systematically as cosmic distance markers. The early years were brutal. The team spent 3 years, from 88 to 91, developing their observation strategy and finding exactly 0 usable supernova. The problem was that supernovae are rare, unpredictable events. You cannot schedule them. Perlmutter's breakthrough was the batch strategy. Observe many galaxies in a wide field. Wait 2 to 3 weeks, observe the same galaxies again, and computationally subtract the first set of images from the second. Any new bright spot is a supernova candidate. This turned supernova hunting from a game of chance into a systematic factory. The High Z Supernova Search Team was co-founded in 1994 by Brian Schmidt, born in 1967, then a postdoc at Harvard, and Nicholas Suntsev, a staff astronomer at Cerro Tololo Inter-American Observatory in Chile. The team took their first data on February 25, 1995, and quickly became fierce competitors with Perlmutter's group. The rivalry was intense and occasionally bitter. with each team questioning the other's calibration methods, data quality, and systematic error handling. Adam Rees, born in 1969, joined Schmidt's team and led its data analysis using a technique he had developed called the multicolor light curve shape method, which used the color evolution of a supernova's light curve to correct for variations in intrinsic brightness. Both teams were measuring the same physical quantity. How far away are distant type A supernovae really, compared to what their recession velocities predict? In a universe where gravity is slowing the expansion, distant supernovae should appear slightly brighter than a simple extrapolation from nearby supernovae would suggest, because the expansion was faster in the past and has since decelerated. All three cosmological scenarios, under serious consideration at the time, involved deceleration. The universe might decelerate forever, but never stop expanding, might decelerate and eventually recollapse in a big crunch, or might decelerate and asymptotically approach a halt. Nobody, and I mean nobody in the mainstream cosmological community, expected acceleration. When Adam Rees ran his analysis code on the high-Z data, assuming a decelerating universe, the code returned a negative mass for the universe. This is physically impossible. Negative mass does not exist. Rees checked his code for bugs. He checked his data for contamination. He checked his calibration for systematic errors. Everything was clean. The data was telling him, unambiguously, that the distant supernovae were 10 to 15% farther away than a decelerating universe would predict. The universe is not slowing down, it is speeding up. Something, some unknown form of energy, with negative pressure, is pushing space apart at an accelerating rate. The high-Z team published first, Rees et al. Observational evidence from supernovae for an accelerating universe and a cosmological constant, appeared in the Astronomical Journal in September 1998. Based on 16 high redshift supernovae plus 34 nearby calibrators at 2.8 sigma significance. Perlmutter's supernova cosmology project confirmed the result with 42 high redshift supernovae in the Astrophysical Journal in 1999. Two rival teams, each convinced the other was probably making systematic errors, forced by their own data to reach the same impossible conclusion. Michael Turner of the University of Chicago coined the name at a meeting at Mount Stromlo Observatory in Australia in 1998. He tried funny energy first, which would have been a much more memorable name, before settling on dark energy, paralleling the already established term dark matter. His reasoning was explicitly strategic. He said, if you allowed this stuff to be called the cosmological constant, we are done. But we absolutely do not know that it is the cosmological constant, and calling it that would make people stop looking for a real explanation. Perlmutter, Schmidt, and Rees shared the 2011 Nobel Prize in Physics. The exclusion of Nicholas Suntsev, who had co-founded the high-Z team and made essential contributions, remained a sore point. Astronomer Royal Martin Rees observed that it would have been fairer and would have sent a less distorted message about how this kind of science is actually done if the award had been made collectively to all members of both groups. Science magazine had already named the accelerating universe its breakthrough of the year for 1998, and the vacuum energy problem, which had been a purely theoretical embarrassment for 3 decades, became an observational crisis overnight, because the vacuum energy is not zero. The hope that some unknown cancellation mechanism sets it to exactly nothing is dead. The actual value is tiny, incredibly tiny, but it is real, and it is positive, and it is driving the universe apart faster and faster. Dark energy, whatever it actually is, constitutes roughly 68 to 70% of the total mass energy content of the universe. You are living in a cosmos that is mostly made of something nobody can explain, and that something is winning. And the gap between what our theories predict and what we observe is 120 orders of magnitude wide. I want to pause here and be clear about what dark energy is not, because there are a lot of misconceptions floating around. Dark energy is not a substance. It is not a fluid filling space, like some invisible gas. It is not made of particles, at least not any that have been detected. It is not dark matter, which is a completely different mystery involving unseen mass that gravitates normally and clusters into halos around galaxies. Dark energy does not cluster. It does not attract. It does not interact with light or matter in any known way except through gravity, and its gravitational effect is repulsive, which is the opposite of everything else we know. Its defining characteristic is an equation of state parameter, W, equal to the ratio of its pressure to its energy density. For a cosmological constant, W equals exactly -1, constant energy density, constant negative pressure. It does not dilute as space expands. Every cubic meter of new space that the expansion creates comes preloaded with the same amount of dark energy as every other cubic meter. The more space there is, the more dark energy there is. The more dark energy there is, the faster space expands. The faster space expands, the more space there is. It is a feedback loop with no off switch. Think about what that means for the far future of the universe. If dark energy remains constant, the expansion will continue to accelerate forever. Distant galaxies will recede from us faster than light, not because they are moving through space faster than light, but because the space between us is stretching faster than light can cross it. They will fade from view, their light redshifted into undetectability, one by one, until the observable universe contains nothing but our local group of galaxies, gravitationally bound together in an ocean of emptiness. Eventually, over timescales so vast, they make the current age of the universe look like a rounding error. Even the stars will burn out, the protons may decay, the black holes will evaporate, and the universe will approach a state of maximum entropy, a featureless, lightless, empty void, expanding forever into nothing. The vacuum wins. That is what the data says. That is the long-term forecast, written in the equations of general relativity, with the observed value of the cosmological constant plugged in. And somehow, it gets worse when you look at the details. Because the discovery of dark energy did not just confirm that the vacuum energy is non-zero, it split the cosmological constant problem into 3 separate crises, each one more disturbing than the last. The first is the old cosmological constant problem, the one that has existed since Zel'dovich's 1967 paper. Why is the vacuum energy so fantastically smaller than quantum field theory predicts? Why is the number not 10 to the 96th, but 10 to the -27th? What mechanism, what symmetry, what principle cancels 120 orders of magnitude of energy and leaves behind only this tiny residue? Nobody knows. Supersymmetry was supposed to help, because in a perfectly supersymmetric universe, every boson's vacuum energy contribution would be exactly cancelled by its fermionic partner. But supersymmetry, if it exists at all, is badly broken in our universe. The superpartners have not been found at the Large Hadron Collider despite decades of searching. and even broken supersymmetry reduces the discrepancy by at most a few tens of orders of magnitude, nowhere near enough. The second is the new cosmological constant problem, which emerged only after 1998. Why is the vacuum energy small, but not zero? If some mechanism exists to cancel the vacuum energy, why does it not cancel it completely? Why does it leave behind this specific tiny positive residue? A cancellation that is almost perfect, but not quite. Off by 1 part in 10 to the 120th is in some ways more disturbing than no cancellation at all, because it suggests a mechanism of extraordinary precision that nevertheless fails at the very last decimal place. What kind of physics could possibly produce that? The third is the coincidence problem, and this one bothers cosmologists more than they usually admit. The energy density of dark energy is roughly constant as the universe expands. The energy density of matter decreases as the universe expands because matter dilutes as space stretches. These two quantities have been evolving at very different rates for 13.8 billion years. In the early universe, matter dominated overwhelmingly. In the far future, dark energy will dominate overwhelmingly. Right now, today, in this narrow epoch of cosmic history, the two happen to be within a factor of about 3 of each other. We just happen to exist during the tiny window when dark energy and matter density are comparable. As Steven Weinberg put it, the old cosmological constant problem is to understand why the vacuum energy is so small. The new problem is to understand why it is comparable to the present mass density. Is this a coincidence, or does it mean something? If it is a coincidence, it is a staggeringly improbable one. If it means something, nobody has identified what. This is where things stood when the theoretical community, having exhausted every conventional approach, turned in desperation to the most controversial idea in the history of physics. Steven Weinberg saw this coming before anyone else. In 1987, 11 years before the supernova results, he published Anthropic Bound on the Cosmological Constant in Physical Review Letters. Weinberg, born May 3, 1933, in New York, shared the 1979 Nobel Prize for electroweak unification, and his 1967 paper, A Model of Leptons, predicted both the Higgs boson and weak neutral currents decades before they were confirmed. He was famous for writing, "The more the universe seems comprehensible, the more it also seems pointless," a statement he meant not as despair, but as an honest reckoning with what physics reveals. He died July 23, 2021, in Austin, Texas. His anthropic argument was simple and devastating. If the cosmological constant were much larger and positive, the repulsive force would prevent matter from collapsing into galaxies. No galaxies means no stars, no planets, no observers. If too large and negative, the universe recollapses before complexity emerges. Observers can only exist where lambda is small enough for structure formation. Weinberg calculated the range. His upper bound landed within 1 or 2 orders of magnitude of the value measured a decade later. The probability of our specific observed value was about 5 to 12%. This was the only successful prediction of any kind about the cosmological constant before its measurement. His 1989 review, The Cosmological Constant Problem in Reviews of Modern Physics, became the canonical reference, one of the most cited papers in physics. Antonio Padilla, at the University of Nottingham, who has spent nearly 2 decades on this problem, calls it one of the most awkward, embarrassing, difficult problems in theoretical physics today. Michael Turner calls dark energy the most profound mystery in all of science. But the anthropic argument needs many universes. A single universe with one value of lambda makes the observation miraculous. An ensemble of universes with randomly distributed values makes it statistical. You need those other universes to actually exist. And string theory, almost by accident, appeared to provide them. In 2000, Raphael Goussot and Joseph Polchinski showed in the Journal of High Energy Physics that string theory's extra dimensions can be compactified in an enormous number of distinct configurations, each yielding different low-energy physics, including different values of the cosmological constant. In 2003, the KKLT paper by Kachru, Kalosh, Linde, and Trivedi provided mechanisms for constructing expanding universes with positive cosmological constant within string theory. Leonard Susskind described these constructions as jury-rigged Rube Goldberg contraptions that could hardly have fundamental significance. Then, in 2003, Susskind himself coined the term the anthropic landscape of string theory. In 2004, Michael Douglas calculated roughly 10 to the 500th power distinct vacuum states. Some estimates go as high as 10 to the 272,000th power. If eternal inflation creates pocket universes realizing each vacuum state, our small lambda becomes statistically inevitable, like Earth being at the right distance from its star given billions of planets. The backlash was ferocious and personal. David Gross, who won the 2004 Nobel for Asymptotic Freedom, called the landscape dangerous and bizarre science, warning it is impossible to disprove. Peter Woit at Columbia, author of Not Even Wrong, wrote that the multiverse functions as an all-purpose excuse for not being able to explain anything about particle physics. Lee Smolin at the Perimeter Institute proposed cosmological natural selection as an alternative. Paul Steinhardt at Princeton, one of the original architects of inflationary cosmology, said that in the landscape framework, literally anything can happen and does happen infinitely many times, making the theory totally unpredictable or equivalently unfalsifiable. And unfalsifiable in science is a death sentence. I am going to tell you what I actually think, which is something I try to do in these videos even when the answer is uncomfortable. I think the landscape might be right. I think the cosmological constant might be an environmental accident, like the orbital radius of Earth, not derivable from any equation. Weinberg drew the parallel to Kepler, who spent years trying to derive planetary distances from nested platonic solids. There is no such law. The distances are what they are because of accidents during the solar system's formation. The cosmological constant may be the same kind of brute fact. Weinberg himself was candid about the emotional cost. He wrote that it would be a disappointment if this were the solution, because we would like to calculate all constants of nature from first principles. But it may be a disappointment we have to live with. And I think that should genuinely disturb you. Not because the multiverse is strange, but because of what it means for the entire project of fundamental physics as practiced for 4 centuries. Since Galileo and Newton, the operating assumption has been that the constants of nature can be derived from deeper laws, that there is a reason the electron has the mass it has, a reason light moves at the speed it does, a reason the vacuum has the energy it has. The landscape says that for at least some of these constants, there is no reason. The value is a roll of the dice. The foundation of reality is not a law, it is a lottery. And you cannot derive the winning numbers from first principles any more than you can derive the winning Powerball numbers from number theory. And if that is true, then the energy physics erased in 1948 was not an inconvenient infinity. It was a message about the nature of existence that we were not prepared to hear. And here is the thing that makes the whole situation even more unstable. The latest data suggests that even the lottery analogy might be too simple, because dark energy might not be constant. The Dark Energy Spectroscopic Instrument, or DESI, is the most ambitious cosmological survey instrument ever built. Mounted on the Nicholas U. Male 4-meter telescope at Kitt Peak National Observatory in Arizona, at an elevation of 6,880 feet. In the Sonoran Desert, it began its 5-year survey on May 14th, 2021. Its focal plane contains 5,000 robotic fiber optic positioners, each one a tiny robotic arm that can be repositioned in seconds to target a different galaxy, feeding light into 10 spectrographs that measure each galaxy's redshift with extraordinary precision. The goal is to map the 3-dimensional positions of 35 million galaxies and 2.4 million quasars, creating the most detailed map of the cosmic expansion history ever assembled. DESI's Data Release 1, published April 4th, 2024, and based on the first year of observations, analyzed over 6 million extragalactic objects across a wide range of cosmic epochs. For a dark energy equation of state that does not change with time, DESI found W equals negative 0.99 plus or minus 0.15, perfectly consistent with the cosmological constant. But when the analysis allowed dark energy to evolve, using the standard 2-parameter model where W equals W naught plus WA times the ratio of scale factors, intriguing hints emerged. The data suggested that dark energy was stronger in the early universe and has been weakening over time at about 2.5 sigma significance. Interesting, but not conclusive. Data Release 2 changed the conversation. Published in March 2025, and based on 3 years of observations, it analyzed over 14 million galaxies and quasars with baryon acoustic oscillation measurements achieving a precision of roughly 0.5% across 6 distinct redshift bins stretching from the nearby universe to redshift 4.2. Combined with cosmic microwave background data from the Planck satellite and various Type 1 supernova datasets, the evidence for dark energy evolving over time strengthened to between 2.8 and 4.2 sigma, depending on which supernova dataset was used. The Union 3 dataset gave the strongest signal at 4.2 sigma. DESI's own official statement was remarkable for its directness. In a field where hedging and qualifiers are the norm, where scientists typically say more data is needed and further investigation is warranted, DESI's collaboration wrote that unless there is an unknown systematic error associated with one or more datasets, it is clear that the standard cosmological model is being challenged. I spent 3 hours reading through their technical papers after that announcement, and what struck me was how carefully they had checked for systematic effects and how little room they found for the signal to be an artifact. This might be real. If dark energy is evolving, if it is genuinely weakening over cosmic time, the implications cascade outward, and each one is worse than the last. The cosmological constant, by definition, is constant. If dark energy changes, it is not a cosmological constant. It is something else, a dynamical scalar field rolling slowly down a potential, the kind of thing theorists call quintessence, or a modification to general relativity that makes gravity behave differently at cosmic scales, or something no theorist has yet imagined. And here is the critical escalation. Neither the anthropic landscape nor any symmetry-based cancellation mechanism can explain a changing dark energy. Those approaches are all designed to produce a single fixed value of the vacuum energy. If the value is not fixed, they fail. The crisis is not just that we cannot explain the number. The crisis may be that the number is not even a number, it is a function. And we do not know the function. And we do not know why there should be a function. And we do not have a theory that predicts a function. The European Space Agency's Euclid telescope, launched July 1st, 2023, and operating from the L2 Lagrange point 1.5 million kilometers from Earth, is mapping 1/3 of the entire sky across 6 years of observations, measuring the shapes and positions of over 1 billion galaxies using both weak gravitational lensing and galaxy clustering. Its first dark energy constraints from the actual survey data are expected in October 2026. NASA's Nancy Grace Roman Space Telescope is scheduled to launch by May 2027 and will provide complementary measurements with its wide-field infrared survey camera. Between DESI, Euclid, and Roman, the next 5 years will produce the most precise measurements of dark energy the human species has ever made. And those measurements will either confirm that dark energy is constant, which would be a relief of sorts, but would still leave the 120 order of magnitude crisis entirely unresolved, or they will confirm that dark energy is evolving, which would deepen the crisis into something genuinely unprecedented in the history of science. And here is where I want to end. But I want to take a moment first to say something about what this problem actually means. Not what it means for physics as a profession or for the next generation of telescopes. What it means for you, for anyone who has ever looked up at the night sky and wondered whether the universe makes sense. The vacuum energy problem is not like other unsolved problems in physics. It is not a missing piece of a puzzle where the shape of the whole tells you roughly what the piece looks like. It is not a question where the answer is probably hiding in an energy range we have not probed yet, or a regime we have not tested, or a corner of parameter space we have not explored. It is a problem where our two best theories of reality, quantum mechanics and general relativity, each individually the most successful scientific theories ever devised, each confirmed by every experiment ever performed in its domain, give answers that differ by 120 orders of magnitude when you ask them the same question. The question is simple. How much energy does empty space contain? The answers are not compatible. They are not even in the same universe of discourse. They differ by more than the number of atoms in the observable universe. And that means something profound. It means that the foundation of modern physics, the thing everything else is built on, the quantum field and the curved space-time that together describe every phenomenon we have ever observed, contains a contradiction so vast that it should, by rights, prevent the entire framework from functioning. The fact that it functions anyway, that QED gives predictions accurate to 10 significant figures while simultaneously predicting a vacuum energy that would destroy the universe, is itself one of the deepest mysteries in all of science. The theory works despite being wrong in a way that should prevent it from working at all, and nobody knows why. I have thought about this a lot, probably more than is healthy, and the conclusion I keep arriving at is this: the vacuum energy problem is not a bug in our understanding. It is a feature. It is a signpost, possibly the most important signpost in all of physics, pointing toward whatever comes after quantum field theory and general relativity. Whatever the next theory is, whatever replaces or unifies or transcends the Standard Model and Einstein's equations, it will have to explain why the vacuum has the energy it has. And explaining that will almost certainly require a revolution in our understanding of reality as profound as quantum mechanics itself was a century ago. The problem is that nobody currently has any idea what that revolution looks like. Active research programs exist, running vacuum models, where vacuum energy evolves with the cosmic expansion. Unimodular gravity, where trace-free Einstein equations prevent certain vacuum contributions from gravitating. Non-local modifications to gravity, sequestering mechanisms that dynamically adjust the cosmological constant. Swampland conjectures from string theory that constrain what kinds of effective theories can be consistently coupled to quantum gravity. None has gained broad acceptance. None has produced a prediction that has been confirmed. The problem has resisted every approach thrown at it for nearly 60 years since Zel'dovich's paper, and there is no breakthrough on the horizon that anyone can point to with confidence. I keep coming back to 1948, to a physicist at a lightbulb factory, inspired by a mumble from an old Danish man who proved in 3 pages that empty space pushes things around, and to 3 brilliant physicists on 3 continents who figured out simultaneously how to make that energy disappear from their equations so the equations would work. They were not being dishonest. They were being practical. They had a theory that produced infinities, and they found a way to get finite, testable, extraordinarily accurate predictions out of it. That is good science. That is science working the way it is supposed to work. You take what the math gives you, you figure out what is measurable, and you make predictions. And the predictions were magnificent, 11 decimal places. Nothing in the history of human knowledge has ever been that precise. But somewhere in the act of subtraction, something was lost, not a number, an understanding. The vacuum has energy. The energy was deleted. The deletion worked for particles. It failed for the universe. And now, 78 years later, we are left with a cosmos that is 68% composed of something we subtracted from our equations in 1948 and cannot put back. In 1948, Pauli called Casimir's prediction absolute nonsense. In 2000 and 2006, the nonsense makes up 68% of everything that exists. The vacuum won that argument. Pauli just did not live to see it. Dirac warned that renormalization was not sensible mathematics. He spent his final years searching for something more rigorous, something that did not require pretending infinities were zero. He published his last paper in 1984, still searching. He died that same year in Tallahassee, far from Cambridge, far from the institutions that had celebrated his earlier triumphs, still convinced that the foundations of quantum field theory were rotten. Nobody has proved him wrong. Feynman accepted a Nobel Prize for a procedure he privately called hocus pocus and publicly called a dippy process and a shell game. He told his students that renormalization was not legitimate. He told the public the same thing in his books. He suspected the whole apparatus was mathematically inconsistent. The apparatus still works. Nobody can explain why it works. Casimir proved the vacuum is not empty. He did it from a factory in Eindhoven, working on the physics of colloidal suspensions, inspired by a mumble from Bohr that nobody else in the room even noticed. His 3-page paper is one of the most important documents in 20th century physics. He never received a Nobel Prize. He received honorary degrees and medals and memberships in prestigious academies, and he lived to 90, and he saw his prediction confirmed to 1% precision, and the Nobel Committee never called. I think about that sometimes. Zel'dovich, the self-taught physicist with no college degree, 3 times hero of socialist labor, designer of hydrogen bombs, and discoverer of accretion disk physics, and inspiration for Hawking radiation, sat down in 1967 and identified the deepest problem in all of theoretical physics with a 2-page paper in a Soviet journal. His calculation is still exactly as catastrophic today as it was 59 years ago. Nothing has changed. The discrepancy has not shrunk. No mechanism has been found. The number is still wrong by 120 orders of magnitude, give or take 60, depending on who you ask. The vacuum has energy. That was established theoretically by Planck in 1911, named by Einstein in 1913, predicted to exert force by Casimir in 1948, and measured to 1% precision by Mohideen and Roy in 1998. The vacuum's energy gravitates. That was proved by Zel'dovich in 1967. The vacuum's energy is accelerating the expansion of the universe. That was discovered by Perlmutter, Schmidt, and Rees in 1998 and awarded a Nobel Prize in 2011. The vacuum's energy might be changing over time. That is what DESI's data from 2024 and 2025 is suggesting at a significance level that is approaching the threshold where you can no longer wave it away. Why the vacuum has energy at all? Why it has the specific amount of energy it has? Why that amount is 120 orders of magnitude smaller than what our best theory of quantum fields predicts? Whether the amount is constant or changing. What it means that the most precisely accurate theory in the history of science requires deleting the most cosmologically important number in the universe before it can produce any predictions at all. Those questions have no answers, not tentative answers, not preliminary answers, not answers that are almost there, no answers at all. The energy of empty space was solved in 1948. The answer was immediately erased from physics. 78 years later, the erasure is still embedded in every quantum field theory calculation performed on every computer in every university on Earth. The answer is still unexplained. The most fundamental quantity in cosmology, the energy that determines whether the universe expands or contracts, whether galaxies form or dissolve, whether complexity emerges or is forbidden, has no theoretical derivation. It is measured, it is confirmed, it is real, and it is the single most precisely unexplained number in all of science. In 1911, Planck found it, and it troubled him. In 1913, Einstein named it, and then tried to kill it. In the 20s, Pauli calculated what it should do, and decided the result was too absurd to accept. In 1948, Casimir proved it exerts force and was told it was nonsense. That same year, Schwinger, Feynman, and Tomonaga found a way to make it vanish from their equations. In 1967, Zel'dovich proved the vanishing was illegitimate. In 1998, Perlmutter, Schmidt, and Rees proved the vanished quantity was real and driving the expansion of the universe. In 2025, DESI began suggesting it might be changing. The vacuum is still waiting for someone to put back what was taken out.